this semester is Max Riegler, who is visiting from University of Brussels, and he will tell us about warm black hole in lower spin gravity.
Yeah, thank you very much for the kind introduction, Zola. And yeah, thank you for everybody who stuck around for this last talk. I'll really try to keep it brief. So what I want to talk about today is some work I've been doing recently together with Tatsuo Asianagi and Stéphane de Tonnet, who are in Brussels as well. And since I know there's a very diverse audience here, I will really try to keep it A, short, and B, very conceptual. So I'll try to avoid any technical details if possible. And people who are interested in more technical details, I would refer to the actual paper. So since this is the Black Hole Institute, I thought I'd actually talk about black holes, and it seemed to be that was a good idea because Avi told me otherwise I wouldn't have gotten a sandwich. So I'm glad I chose this subject. So I think that part I wanted to motivate for anybody in this audience to study, but the warp part and the lower spin part, gravity part, might be much more unfamiliar to most of the people. So first I want to try to motivate to explain to you three keywords that will appear through this short talk. And the first one is basically warped ADS3, and I put here in brackets also the black hole part. So I will explain to you very briefly what is that, why it's interesting to study. The second keyword is what is called a warped CFT. And again, here I want to briefly tell you what it is and why it is interesting to study. And the third keyword is actually this lower spin gravity part. So what do these three keywords have in common? Well, since I'm a high energy theory particle physicist, I'm interested at symmetries. And what these three guys have in common are basically their symmetries. So all of them are related to SN2R plus U1 symmetries, basically. So first of all, what are warped ADS3 spacetimes? As the name suggests, they're basically deformations of anti-de Sitter spacetimes in 3 dimensions. So you basically take a space-like chiral Killing vector and deform the metric with that. You can do it with the BTC black hole, and you get a space-like warped black hole, for example, if you deform it in a certain way. Or if you just take ADS3, you end up with a warped ADS3 spacetime. There are different kinds of warping that have different kinds of names. And what's interesting about this warping is that it breaks down the usual SO2-2 symmetries of ADS down to SL2R plus U1. So what it does, it changes both the isometries as well as the asymptotics of the spacetime. And why is it interesting to study? Well, because these warped ADS spacetimes appear as near-horizon extremal geometries, namely of extremal Kerr black holes. So these geometries might be very interesting to study Kerr black holes in the end, like very special Kerr black holes. The second guy in the game here is a warped conformal field theory. Again, it's basically a quantum field theory that has its global symmetries SL2R plus U1. And what makes this very similar to a CFT is that it also has an infinite number of conserved charges. However, what makes it different is that the resulting quantum field theory is in general a non-relativistic one. So this is some very interesting, so that's has some very interesting consequences. And why is it interesting to study that guy? Well, I told you that the asymptotics of this warped ADS3 spacetimes also change in comparison to ADS. And if you look at holography, you can interpret these warped conformal field theories as possible dual quantum field theories for these warped spacetimes. So if that works out nicely, you could use these guys to study warped ADS3 spacetimes and in turn also Kerr. So this is a possibility. I'm not saying this has to be the case, but this is a possibility.
Can you please explain what you mean by non-relativistic field theory?
Non-relativistic really means that you have something like, so in this particular example, if you look at the scaling symmetries, for example, not both coordinates, if it's a two-dimensional conformal field theories, then not both coordinates scale the same way, but one scales in a different way. So if you want to have something like a preferred time axis, so in that sense.
It's got a Galilean symmetry, not a...
Kind of, similar in that regard, kind of. The third guy here, that's the lower spin gravity part, that is a so-called Chern-Simons gauge theory. I'll explain to you in a second what I mean by that. Again, with a gauge algebra that is SL2R plus U1. And why is it interesting to study? Well, you might already see where I'm going here. This theory provides a particular realization of warped ADS spacetimes in a very simple setup. Since this is a Chern-Simons gauge field, that means the theory is topological. So if you want, this theory is basically what Einstein gravity in 3D is for holography, so for ADS3 CFD2. This guy could be the same thing for warped ADS spacetimes. Because in all other examples, if you wanted to have a theory that actually allows for warped ADS solutions, you needed something like high derivatives or additional matter content. So that's why that guy is interesting. So that basically was the what and the why part.
So is it different from topologically massive gravity?
Yes, it's different from TMG, yes.
How?
It's different in the sense that you do not have any higher derivatives in the game, but there's one thing I have to mention here. This guy is basically only known at the level of the Chern-Simons gauge theory. So at least as far as I know, or to the best of my knowledge, I cannot write down anything in a second order formulation at this theory. So it seems to be something very different than TMG that has any higher derivatives, but aside from the Chern-Simons reaction, nothing more is known as of that from that thing. And what is not known as of that, there's a very nice paper developing all the mechanics and the things you need to know about this low spin gravity paper, but they only showed that you had warped ADS spacetimes. So that low spin gravity supports warped ADS spacetimes, but the big question is, what about black holes? Because if you have black holes, by holography you would have a very nice tool to study warped conformal field theories at a finite temperature. So that helps you to learn something completely new about possible quantum gravity effects or warped conformal field theories in general. And that's basically what we tried to do in that work. We tried to see, okay, can this theory of low spin gravity actually accommodate black hole solutions? And if yes, how do you describe the thermodynamics? And you will see in a second why this is kind of a non-trivial question, because the whole story about this Chern-Simons gauge theories is that you lose all your geometric intuition that you usually have from GR. Because you're basically just working with the gauge theory, you kind of not know what to do in the beginning if you not already know what you're supposed to do, kind of. So that was the big question here, okay? We had to figure out what we had to do in the beginning. So, first of all, what is a Chern-Simons gauge theory and why is it interesting to study? Usually, if we work with GR, we work in a second order formulation. So we have the metric as our dynamical field, and that's how we describe gravitational physics. But for some purposes, it's more convenient to actually have something like a local Lorentz invariant laboratory frame of this form. So you have a field bind, and this should be the Minkowski metric. And if you have that guy, then alternatively, you can describe GR in terms of this field bind and a spin connection that takes care of the Lorentz transformation in your local frame. That's basically, you change from a second order to a first order formulation. And what's special about 3D is that you can dualize that guy. So I'm sorry for writing a formula, but there's sometimes no way around writing formulas. So this is a three-dimensional Levi-Civita symbol. And the nice thing is that you can now recombine your Dreibein, in that case, and the spin connection into the same gauge field, basically. And then you can show that something that is called the Chern-Simons action, and I'm writing it here in a very special way. So this will be, I think, the longest thing I'm going to write down in my talk. So bear with me, please. That this is basically the same as the Einstein-Hilbert-Palatini action up to boundary terms. So if you reinsert what I wrote here for A into that guy, in the end you will end up with the Einstein-Hilbert-Palatini action, and this K basically encodes Newton's constant. So that's the rough idea what a Chern-Simons gauge theory is. And the pro of that of this reformulation is that you can use all the tools that you know from gauge theory to tackle your problems. It's sometimes computationally more efficient to use this kind of formalism, and there's very easy extensions to setups that are relevant in the context of high spin symmetries. So I won't go into details about the high spin story, but those are some pros of using that formalism. The obvious downside is you completely throw away geometric intuition, and it works only in 3D. So those are some pretty obvious drawbacks of that story. But if you're mainly interested in 3D, that's a very nice thing to actually work with on a practical level. Okay, now what is lower spin gravity? So the lower spin gravity action in terms of this Chern-Simons action is nothing else than a sum of two Chern-Simons actions with couplings K and kappa, where the A here is basically a gauge field value in SL2R and the C takes values in U1. That's basically all there is. Now you might ask, okay, that sounds nice, but why? That's usually the first big thing, and I completely agree with you that that is a very good question, because it's not at all obvious if you just write down an action like this to what this should correspond to or why this should be relevant to study, right? But in 2014, Diego Hoffman and Blaise Roulier, just let me give you the paper number as well for that, wrote a very nice paper. So that's not the title of the paper, but that's one of the contents of the paper. They were working at warp geometry, 14.11.06.72. So they were basically concerned with the question, okay, since these kind of warp conformal field theories are non-relativistic, they should also not couple to Riemannian geometries. So right, if you want to describe these in terms of on a curved spacetime, to what kind of geometry do warp conformal field theories couple to? And they basically started out with, okay, what are the basic, excuse me, the basic symmetries of my warp conformal field theory, and to what kind of geometry do these correspond? So that was basically the main point of their paper, and they found something that is called warp conformal geometry. And then I thought, okay, if at my boundary of my spacetime I have a warp conformal field theory that is described by a warp geometry, if I want to have a holographic dual description thereof, what I do, I try to extend this geometry into the bulk. I require that certain structural equations are satisfied, and then I should end up with a proper holographic dual theory describing the correct boundary dynamics in my warp conformal field theory. That's what they did. That's basically step number 2. So extend the geometry into the bulk. And when they did that, they saw, okay, these structure equations that I needed in order to satisfy, like these structure equations that they wanted to have satisfied, can basically written in terms of a Chern-Simons theory that has two gauge fields that are now calling B bar, B and B bar, and there were 3 constants appearing that were needed for this extension. So this basically corresponds to time rescaling, this alpha. This beta encodes the warpings that I mentioned here, and the C encodes the ADS radius. So that's basically what these numbers correspond to. And then they saw, okay, if I recombine these 2 gauge fields using these 3 numbers in a very special way, then what I exactly end up is what I wrote here. So if you want, they found a way. First of all, they derived how should the geometry look like. They found basically a way how to write the correct field lines and the spin connections in the bulk that should reproduce a warp conformal field theory and warp spacetimes. And then they did a very elegant rewriting of their story where you kind of lose the intuition for the geometry in terms of these SL2 plus U1 gauge theory. That's basically the idea how they found that kind of theory. Okay, so now what is our challenge? So I briefly mentioned that. The challenge in our paper, or like in our work, was, first of all, we wanted to find boundary conditions that include black hole solutions. That was the first thing. Then these boundary conditions should have asymptotic symmetry, so that's an asymptotic symmetry algebra that has the correct symmetries to be a warp conformal field theory. And then that was the most tricky part, how to translate the geometrical intuition that you have into the Chern-Simons gauge field. So what do I mean by that? Let me give you one explicit example that also gave us a little bit of a headache, is if you want to describe a black hole with sensible thermodynamics, usually you would require that the Euclideanized version of the black hole does not have conical singularities at the horizon. That's a geometric statement that you can make, and this is necessary. How does it translate to Chern-Simons gauge theory? In Einstein gravity, you know exactly how it works. You know that it basically translates to the holonomies of the gauge connections around the thermal cycle. The holonomies have to be trivial in that specific sense. So we had an intuition kind of what to do, but we had to find out the specifics on what to do. So how does the warping basically pop up in that case? And let me tell you, we found boundary conditions that include these black holes. We found asymptotic symmetry algebra, and we computed the thermodynamics. So let me briefly, I think I have 5 minutes left, or like 5 to 7 minutes. So just to give you an overview, what do I mean by all these statements? Because sometimes some people might be very familiar with that story and might be very bored, but some people might be completely unfamiliar and say, okay, what do I mean by the words I'm using? So with boundary conditions, I'm basically referring to the behavior of the gauge field. Sorry, and I haven't given you a picture of what kind of manifold we're actually working on. So we're assuming we have the topology of a cylinder. Just didn't know what the labels rho, phi, and t here mean. So boundary conditions mean how do my gauge field behave very close to the boundary, or to be more specific, at the boundary. And what do I mean, how does one usually compute the asymptotic symmetry algebras? Well, one looks for all the gauge transformations that at the boundary leave these boundary conditions invariant. So that means, let's say you have some free functions appearing, and the same for C. Let's say you have some free functions appearing in your boundary conditions, and it means that the most that these gauge transformations are allowed to do to change the form of the free function, but not their power in a row, basically. So that's what these guys do. And once you know what these kinds of gauge transformations look like, you have a way of computing the asymptotic charges corresponding to these gauge transformations. Now, why are these guys interesting? Well, first of all, their Poisson bracket tells you what the asymptotic symmetries are, and what's more, like from a physical point of view, what's more important is they tell you for what, in the case of a black hole, what is the mass and what is the angular momentum. That's what's basically what the physical content was, what these two guys encode. And if you do that, you find actually what you should find. You find that the asymptotic symmetry algebra at the boundary, for the boundary conditions that we wrote down, gets enhanced to infinite dimensional versions, basically of SL2R and U1, and to be more specific, of infinite dimensional centrally extended version of Virasoro and U1. So if you remember the talk by Blaža last week, where he mentioned like central extensions and central charges, and the Virasoro algebra, that popped already up there, basically. Okay, now how do we go about the thermal entropy? There are many ways to calculate the thermal entropy, but for our case, the easiest way to calculate the thermal entropy, or the most intuitive one, was to basically integrate the first law of thermodynamics. Now, how did we go about this? Well, mass and angular momentum we could basically extract from the charges. That's nice. But what the more challenging question was, how is the functional dependence of the inverse temperature and the angular velocity in terms of mass and angular momentum? That's usually something that the absence of a conical singularity tells you exactly how these relationships look like. And in our case, I told you already briefly, in the Einstein gravity case, you know that you can get these relations by requiring that the holonomies around the thermal cycle are trivial. And in our case, we made a very similar assumption, if you want. And I promise this will be the last long formula I will write down. So basically, our assumption was the following. where h is given by beta over 2 pi, a in the phi direction is basically the that's t in the t direction, plus omega d phi c a phi. And the barred part is basically the same, but you replace a with c. So that's basically what h and h bar is. And these are basically the holonomies around the thermal cycle for a rotating space like warped AES black hole. That's what we assume. That's basically the statement that the holonomy of the SL2 part is trivial. That statement for the C part is a little bit less trivial because we thought, okay, our inspiration was, since there is a warping happening on the level of the spacetime, maybe there's also some kind of warping on the level of these holonomies. So at this point, this gamma was an unidentified number, and we thought, okay, we make an assumption and see what happens. So at the moment, let's bear with that. And if you make that assumption, you get some very nice expressions for beta and omega, and also a very nice expression for the thermal entropy that is very simple. And for some people who are familiar with conformal field theory, a part of this formula might be very, very familiar. Sorry, let's forget to put this, let's write K. Now, why we were happy with such a result? Well, this is basically what you get for a space-like warped black hole in general. That's nice. Then we thought, okay, I made the statement before, I want to have a warped conformal field theory at the boundary, so I would like to try to compare this formula with what I would get if I would try to compute the thermal entropy of a warped conformal field theory at a finite temperature. Only thing is, if I want to do that, I have to know what the vacuum is of my solution. So that was the second question, big question we had to answer, how to get the vacuum in this Chern-Simons formulation. And again, our answer was very similar to what we wrote here. We said, okay, the vacuum is given by the holonomy, that the vacuum is defined by the holonomy around the phi cycles. And we assumed that the holonomies around the phi cycles are warped trivial. Basically, that's what we call them. So you see, it's basically the right-hand sides coincide with what I wrote here. So again, this is a second kind of assumption that we made. This assumption gives you some values for the mass and for the angular momentum, for the vacuum values. And if you plug that in the expressions you know from warped conformal field theory, you end up with exactly that expression again. So that's a nice cross-check. But let me stress, from purely Chern-Simons perspective, these two are very nice and maybe natural guesses, but I have to prove kind of that these make sense, right? Because otherwise everybody could say, I mean, it's like a catch-22, right? I make an assumption to get what I want, and because I get what I want, I think the assumption is correct. So that's not a good way to do things. So there are various ways how one can check these things, and we did a number of them. And this will be basically the last thing I want to talk about. So what are the checks? So one independent check is to compute the holographic entanglement entropy in this setup. And if you do that, you can take the extensive limit. So the limit where the entanglement entropy becomes extensive. And then one can basically, in this limit, directly read off the thermal entropy. And without any surprise, in this limit, what you get to the thermal entropy coincides exactly what we have here. Then there's another thing one can do. So that's basically what, in my opinion, is the closest to the area law in a geometric picture. One can wrap a Wilson line around the horizon, basically the trace of a Wilson line. And this is equivalent to computing the thermal entropy of the system, and this again gives you this expression. So those are two Chern-Simons ways to check that both these assumptions as well as this expression for the thermal entropy actually make sense and is true. But the third one is to actually have the metric formulation. And that's again thanks to Diego and Blaise, who worked at that nice paper. we knew exactly how to translate the Chern-Simons expression that we had into a metric. And once you have a metric and you know, it looks weird, it's just in a gauge or in a coordinate system that doesn't look like very much like a warped ADS black hole. But since you know it's a space-like warped ADS black hole from these considerations already, you know it's just different, just a weird kind of coordinate system that you use. And once you have that, you can compute, first of all, the inverse temperature as well as the angular velocity. And we found again, that's very nice. This matches exactly what we got for beta and omega, assuming this. And what it did in addition, it fixed gamma. So the metric formulation told us precisely what gamma was. This was something that we could not pick up from the Chern-Simons formulation. In the beginning, this was very frustrating from a Chern-Simons point of view, because you start out with two parameters, those are basically your U1 and your SL2 Chern-Simons level. And this guy just popped out of nowhere. That should not happen in a good theory, right? You should know what your parameters correspond to and where the values come from. And the metric formulation told us what gamma was, so this was very nice. And in addition, also this, what I wrote here, this condition that the vacuum is given by basically the condition that the holonomies around the phi cycles are trivial. Usually in the metric formulation, if you would ask me, okay, how do you compute the vacuum, or how do you find out what's the vacuum of a given black hole solution, I would say, okay, first I compute the Killing vectors of my solution. I found that there's, in that case, 4 Killing vectors. However, only 2 of them are globally well defined. And the 2 of them that are globally well defined are obviously the one that give you mass and angular momentum. And only the other 2 get globally well defined for the values of mass and angular momentum that correspond to the vacuum. And in this case, we could compute again the Killing vectors. So I have to stress, like we just computed it in a weird gauge. Of course, the Killing vectors for space-like warped AES black holes have been found earlier already as well. And we could explicitly check if we insert the values that we got for mass and angular momentum from this condition in Chern-Simons formulation. Only for these values, the 4 Killing vectors that space-like warped AES black holes have are globally well defined. So we see the metric formulation in the end gave us a concrete way to check the assumptions that we made on the Chern-Simons level, that what we did was indeed correct. And in addition, I also have to stress, this story, it's very tempting, like if you just ignore this part, and if you have this Chern-Simons formulation, you say, oh, that's very nice, I have a Chern-Simons theory, that thing has an entropy, there's a non-trivial holonomy around the horizon, so it's very tempting to call this a black hole. But at least in a Chern-Simons language, I would say one should be very careful with calling things black hole without having a metric formulation, because how black holes are defined usually are geometrical statements that we use, right? So in that case, having the metric formulation actually gave us the confidence to call the solutions that we have here actually black holes. Okay, and with that, I hope I didn't bore everybody too much. I hope everybody's still awake, and that's basically what I wanted to tell you. Thank you very much.
So these are the same metrics that you get that we call warped BTZ black holes in topologically nice gravity?
Yes, for certain values, that's a funny thing. For certain, if you choose these, so if you choose these, so I briefly wrote down these 3 numbers, right? These 3 numbers A, B, and C. Then the metric you get is a metric that solves the TMG equations of motion, for example. Yes.
And that's funny because those are higher derivative theories.
Exactly. That's from
yes.
Yes.
And so these metrics, they're the ones that you get from taking a curved black hole, going to the near horizon at fixed theta?
I think so, yes. Usually, yes.
Same thing, right?
Yeah.
Yes.
Is warped black hole a solution of topology massive gravity, new massive gravity, a lot of theories?
Yes. But the good thing about this is that since it's a Chern-Simons theory, it's purely topological. So on the level of the Chern-Simons theory. So that's why I think, it's nice to have a simpler theory that allows for black hole solutions in comparison to TMG or NMG, for example.
My question: why don't you do directly everything in metric then?
That's a very good question. Yeah, so there was one. So I personally like to work in Chern-Simons because there are many new things to learn. And but one personal thing I wanted to study with this is So if you know how to describe a space-like warp black hole in a Chern-Simons formulation, you might be a little bit brave or a little bit naive and try to construct something like higher spin extensions thereof. So let's say you endow your space-like warp black hole with charges that are like with additional charges to mass and angular momentum. And that was for me one of the main things you can do, because higher spin theories in the metric are notoriously complicated, like very, very complicated to work with. But in the Chern-Simons formulation, almost trivially to work with. I mean, trivial is a hard word to say here, but it's much, much, much less complicated in comparison.
It goes back to using the holonomies to define the black hole.
Yes, exactly. That was the point where we wanted to see what the holonomies are, because if you want to try to describe something like a high spin extension of this black hole, again, you have to ask yourself the question, what is a thermodynamically sensible way of writing down your black hole, right? And in that, what you want in the high spin context is that if you turn off the high spin charges, you end up with your spin 2 black hole again. And that's basically encoded in the holonomies. So we wanted also, like if you would write down a high spin version thereof, we wanted the holonomies of this high spin version are the same as in the spin 2 case. That's basically the logic how this usually works in the Chern-Simons formulation. That's exactly why we wanted to see what the holonomies are, because it's a very good question, like why didn't we do it in the metric, why didn't we just write the Wilson line? We wanted to explicitly know what the holonomies look like in order to be able to do an extension to high spins, for example. But again, this is something very naive, I have to say. I just thought it might be nice to have something like this.
Thank you very much, Max and Shiva.